Deploying reinforcement learning policies on humanoid robots is risky. Small mismatches between simulation and the real world can lead to confident but catastrophic failures. In this work, we present RAPT, a lightweight, deployment time system for detecting and diagnosing out-of-distribution behavior in humanoid robots. During real-world deployment, we encountered a failure caused by a subtle distribution shift. A small change in the physical ball size during a throwing task led the policy into an untrained regime, triggering a high-energy and potentially catastrophic behavior. This motivated the need for a system that can detect when a policy leaves its training distribution and explain why. We start with a trained reinforcement learning policy. In simulation, we execute this policy across thousands of parallel robots for approximately 1 minute, collecting a large dataset of nominal execution only. This data is used to train RAPT, a lightweight recurrent probabilistic model that learns the spatio-temporal structure of normal behavior without any anomaly labels. At deployment time, a short calibration phase either in simulation or on real hardware is used to set 3 statistical error thresholds that account for sim-to-real shift. During execution, RAPT runs online alongside the policy, monitoring predictive deviation at high frequency. When an anomaly is detected, we apply integrated gradients with backpropagation to time to compute temporal saliency, revealing which observations and when caused the deviation. These attributions exhibit characteristic patterns for different failure modes, enabling interpretable root cause analysis by a human operator or a downstream reasoning model. We evaluate RAPT across 4 challenging humanoid tasks in simulation: velocity tracking walking, 2 motion mimicry dance tasks, and whole body dynamic throwing. Here we show nominal real-world executions with RAPT running online. Despite external pushes, no false positives are triggered. This robustness comes from training RAPT on domain randomized nominal data, allowing it to ignore expected disturbances while remaining sensitive to genuine anomalies. In this citizen example, a blind policy encounters an unmodeled slope. Without RAPT, the robot rapidly destabilizes. With RAPT enabled, the anomaly is detected early and triggers a safe recovery behavior, walking backwards to avoid further failure. Not all out-of-distribution events are visually obvious. Here, we introduce a gradual sensor bias affecting IMU and motor readings. Although the robots appear normal, RAPT detects the accumulating deviation over time, with different robots flagged at different time steps as they drift out of distribution. This clip shows a real-world deployment with a 7.5 kilogram payload, far beyond the 3 kilogram maximum seen in training. Along the bottom are the commanded walking velocities, while the center plot shows the minimum distance to the calibrated anomaly threshold over time. On the left, we visualize post-hoc temporal saliency computed via backpropagation through time. Several seconds before failure, RAPT attributes the anomaly to hip pitch and waist roll, consistent with the robot leaning backward and laterally under excessive load. As the robot continues moving despite near-zero velocity commands and its gravity-aligned roll drifts, RAPT cuts the policy before uncontrolled behavior occurs. We observe similar early detections across a range of real-world anomalies, including heavy payloads, deformable terrain collisions, and external pushes. In each case, RAPT intervenes before the behavior becomes unsafe. Beyond stopping, RAPT can trigger alternative recovery behaviors. Here, anomaly detection autonomously initiates a backward walking response, naturally increasing clearance and avoiding collisions. We also report failure cases. In this example, a rear collision is not detected, highlighting current limitations and motivating future improvements in sensing and coverage. In summary, RAPT provides a lightweight, interpretable, deployment time measure of centurial mismatch for humanoid robots. By detecting and diagnosing out-of-distribution behavior, it helps prevent silent failures and supports safer real-world deployment. Thanks for watching.